Uh, so little bit logistics before we start. So test 2 is on 29th, that is this Thursday. Midterm review session, the exact timing will be shared with you guys on Piazza. Mostly it will be on Zoom like last time. And please sign up for one-on-one to prepare for the exam. And I think homework 4 grades are already out. Okay. Is there any questions before we start? Cool. Let's start. So today we will look at these two categories of problems: divide and conquer and backtracking. So we'll go over one problem from each of this domain, and we'll see how to approach those problems. So this first problem that we are going to solve is counting inversions. So you're basically given an array T, and for every index I less than j, you want to find all such pairs where T of I is greater than T of j. Okay. So for example, we can see this array, and also one thing is given to you that all elements are distinct integers from 1 to n. Okay, so for this input, basically you will have 3 pairs where T of I is greater than T of j for every I less than j. Okay, so you basically have to give the count of these pairs. So one obvious solution would be to just do a brute force, like iterate over the whole array, and for every I, check out all the j wherein this condition satisfies, right? And you just simply add on the counter every time you iterate over it. That will take O of n square. So there is a better approach. So the hint would be a divide and conquer algorithm, which basically you will divide your array into multiple sub-problems and somehow you merge them to make the exact count. So maybe you can take a little bit of time, discuss with your partners, and then we can discuss about it. Okay, just think a little bit about it. And let me know if you have any question. Is this brute force algorithm clear? Okay. Any hints or like any idea? So we somehow want to make an algorithm which works better than O of n square. That's fine. Should we proceed? Okay. So since we are trying to solve it using divide and conquer, so we'll have these 3 things that we will break our problem into. Okay. So first, what we'll do is we will divide our array into multiple sub-problems, and then we'll do the conquer step. That means basically kind of merging all the sub-problems that we have created, and then recombine all the results. So let's take like what motivates the solution. Imagine this to be a single one big array, this blue and red thing on the top. So what we have done is we have broken down that array into 2 parts, left and right side, okay, into 2 equal parts. And what we are trying to do is like we are trying to find the number of inversions in the left one and the right one separately, okay, and we will sort it afterwards, okay. And while we are merging these 2 arrays after sorting, we will again keep track of like how many inversions we are making. And it turns out like what we are basically doing is when we merge these two arrays after sorting it, we will keep track of the total number of inversions. That means so do you guys remember the merge step in the merge sort? Like you have two sorted arrays and you try to merge them together into a bigger array, which is also sorted, right? You use two pointers and then you keep moving forward, and every time you find a bigger element, like you keep moving things around, yeah? So here also we are doing the same thing. So let's take a look at these arrays here. So this 3 will be moved to this position, and we will calculate by what amount this 3 is getting moved to, okay? So it turns out like 3 here is getting moved by 4 units to the left side. So that means total number of inversions in the merge step is 4, okay? Similarly for 6, it turns out to be 2. For 7 also it turns out to be 2. And for 9 it's 1. For 11 and 12 they are in the exact same position, that's why it's 0, okay? So what we do in the end is like we basically add this thing here, and the inversion here, and that will be our total answer. So this is kind of like a motivation. So this thing works, right? You can see like if we are somehow able to find the correct inversions for left and right side, we will get the right answer. Does that make sense? So right now we are still treating that inversion on top of it as a black box, but once you have a left and right array and you know the inversion numbers for both the arrays and you sort them somehow, and when you combine them you actually get the right answer, right? Okay, so we will see like how this motivation is going to help us further improve the solution. So right now we just saw one level up, right? Like from the array we just broken down into two pieces, and that's what we looked at. But we can keep doing it until we have a single element in the array, right? That's basically what generally a motivation of divide and conquer is, and that will somehow be our base case. So let's see like how we will. So we will do that. So the idea is basically similar to to this merge sort. I think it is very similar to that. Only thing that we update is in the merge step. Like when you are moving elements around, you keep track of the number of steps by which like the elements is getting moved to the left side, and you keep adding those things. Yeah. So let's see. So first thing is base case. So base case would be when you just have a single element. In that case, there are no inversions, right? For a single element, it stays in the exact position, so nothing happens there. So how do we divide this array? So this is the array that we are interested in, 1, 2, 4, 5, 8, 10. So we keep dividing it until we get these single elements on top. This is just divide step. I think it's you guys are very familiar with it by now. We do this in like a lot of different algorithms. So this is how the algorithm goes. So first we will get the inversions from A, the left half. Then we'll get the inversions from B, the right half. And this A and B, they will be the sorted arrays. Okay? And then we'll combine this into a bigger array C, and the inversion of that bigger array is counted by this inversion C, is stored in inversion underscore C. Okay? So we are basically making two recursive calls here. Exactly what we said, right, in that example earlier. And in the merge step, we are calculating the exact inversions we take to merge these two things. And in the end, we just add these three things up. It's exactly an algorithmic way of representing what we just saw in an example earlier. So in counting inversions, what we did, like we were interested in like whenever we are moving an element from B to the left side, we are keeping track of like by how many units it is getting moved to. That's right? So this merge step is exactly similar to that merge sort. We will have two pointers and we'll keep moving them on the right towards the right side until one of the array is completely traversed. Okay, so this condition basically implies that. And if element in A is less than element in B, we basically just append that to C, and we update the index of left array. When the other thing happens, that means the element of B is less now. That means we have to move it towards left, right, somehow. and by how many units will we be moving it? It will be the number of elements left in A, right? Does that make sense? So we are moving that element in B towards left. That means all the elements in A are going to be on the right side, right? But that's the condition, right? So that means everything on the right side is basically a pair which satisfies the condition that we are interested in. Does that make sense? So we are just basically just adding that number up. So this thing here, the underlined thing, is nothing but this thing here. That is like size of A minus the current index. That will give us the remaining elements in A. And rest is similar. So once a particular array is like completely traversed, the other array will be appended to the main vector C, and we'll simply return this array C and the number of inversions. Is it clear? Do you have any questions in this one? Yeah. Mm-hmm. Okay. Let me see if I can give you that intuition here. Okay. So let's assume two things. Let's assume that somehow we are able to get number of inversions in the left array and the right array as well. Okay. So right now in left we know like what the total number of inversions are. Same thing for the right one. Now the challenging thing happens is when you combine these two things, the pairing, it changes a little bit, right? Because this 4, it hasn't seen anything in this array at all, right? Or this 8, it hasn't seen anything in that in that red array at all. So when we merge these two things, that number should be made aware that it is actually looking at a smaller number, right? So anything smaller than 4 will be part of that count, right? So what we are doing is, so when we combine this step, so let's say when we are moving this 3, it will be between 2 and 3, right? Between 2 and 4. It will sit somewhere here. So every element greater than 3 will be a valid part of that condition, right? Because 3, 4 will be a pair, 3, 5 will be a pair, 3, 8 will be a pair, 3, 9, 10 will be a pair. So when you move this 3 to the left side, we are basically adding these 4 elements. Does that make sense? So because our current index is at this pointer 2, so the remaining items in that array will be given to you by like subtracting this whole length by this thing. So it will give you this value. Does that make sense? So that's how we are like keeping track of like how many elements are on the right side. I hope that clears it up a little bit. Okay. Yeah. Yeah. So initially when we start from 1 and 3, right? So when we compare, we see that 1 is smaller than 3. So we simply increase the index of that array. We'll go to 2. And then we'll again compare 2 and 3. The same thing happens. You will go to 4. But now what happens is like 3 is smaller than 4. So you have to move 3. So you will move 3 before 4, right? And when you do that, you have to count like how many elements are there which are bigger than 3. Because you are not interested in these things anymore, because that's already part of this inversion equals to 8. Yeah? Cool. Any other question? Okay. Where were we? So yeah, so we have simply flipped this tree, and we'll go in this direction. Okay. So what happens is like we combine 1 and 5. This is the combined step. Nothing changes, right? 1 and 5, they are in the exact same position. So no inversions. Same thing for 4, for 8 and 10 and 2 as well. Nothing happens, right? They are still in the exact same positions. But when you combine this array and this array, 4 is changing its position. It's no longer at index 2, it is moving to index 1. So that means the total number of inversion happens in that case. Similarly, for this 2, it is moved by 2 units towards left. So you add 2. So yeah, you keep doing that until you get your whole array and you return the answer. Is that clear? PA and PB. This thing? These are the index. So these are the so look. Let's take a look at this thing here. Uh, so when you start doing your merge step, you initialize these two variables. So your PA is equal to PB is equal to 0. Okay. So it represents these two pointers. So at every point you keep iterating these things towards right side based on the conditions. So these variables, it keeps track of where exactly you are in those particular arrays at a given time. Is that clear? So what about the runtime? It would be very similar to the merge sort, right? Anyone want to like explain that? What will it be in terms of like number of sub problems and then merging step? Yeah. Yeah, that's right. Why? Would you like to explain that a little bit? Uh, it will still be linear, the merge step. That's right. Like within the linear thing, these things are constant for every. That's right. That's right. So you are saying like the merge step is big O of n, right? What about the sub problems? How many sub problems do we have here? Right. So we have, so B would be equal to 2, right? And D will be 1. So the runtime would be something like T of n equal to 2 T of n upon 2 plus big O of n raised to 1. So it comes in the category of, which category? A equal to B raised, A is equal to B raised to D. And it will be n raised to D log n. I hope I'm right about this. Okay. But yeah, it will be n log n. Yeah. Master theorem. Okay. Any questions in this one? Yeah. Is this the slide? Yeah. Yeah. Because when they are equal, we are not interested in those elements. And anyway, we are given that the elements in array are distinct integers. So they will never be equal. Sorry, I didn't get the last thing that you said. So we'll never have an equal sign in this one because the condition itself was that every element in the array is distinct. And that inversion thing happens only when, yeah. Okay. Yeah. Any other question? Okay, so we can move on to the different problem. Okay. So we will try to solve Sudoku. How many of you are aware about this puzzle? I guess everyone, right? So okay. So I will still introduce it a little bit for those who don't know it. I don't think there is anyone who don't know it already. But what happens is like you have a 9x9 board, and that board is divided into like 9 different grids. So each of the digits 1 to 9 must occur exactly once in a given row. Same thing happens in a given column, and same thing happens in that given small grid of 3x3. So it will look something like this. So So what generally happens is like you are given something on the left side, some things are filled for you and some things are blank. You basically have to fill all those blank things. Okay, so we'll see like how to solve this problem. So what do you guys think, like how to solve this one? Yeah. Okay. Yep. Interesting. Maybe that would work, but it will require a little bit more work in that case. Think in terms of backtracking here. Like, don't worry about the time complexity for now. It can be as worse as possible. Like, you have like a lot of time on your hand. How would you solve this one? Hmm. Hmm. Yeah. That makes sense. That is one way. Like if a person is looking at it for the first time, that's how he would solve, right? They will choose a random blank spot, and they will try to fill it up with all the possible combinations from 1 to 9. That's right. So you fill one thing, and then you go and fill the other thing, and then you check if these things are compatible, or like if they are valid, right? If they are not valid, you go back to the previous one, you erase it, and then you move on to the next element, right? That's how like generally we solve, right? That's not how we generally solve, but that's how someone who is doing it for the first time would do it, right? Yeah. So let's see how to write that algorithmically. So yeah, so we are given k empty cells, and we can choose a number filling an empty cell, and then we'll get a board with k minus 1 empty cell. So like once we select a particular cell, we fill it. After that, we'll have k minus 1 empty cells, right? That's what it is saying. So it is kind of like trying to like make a recursion thing. Okay. So initially we start with a k blank Sudoku. We fill something, then we'll end up with a k minus 1 empty cells, right? And then we think about the constraints when choosing these numbers. And constraint is just simply from 1 to 9, right? That's it. These are the only constraint, and the other constraint are like everything in the row should be distinct, everything in the column should be distinct, and everything in that small grid should be distinct. Yeah. And if you keep doing that, and eventually it will return a valid answer, right? So what is the base case? So if we keep doing this, eventually we'll end up with a Sudoku completely filled. Only thing that we have to do is like just check if it is a valid Sudoku or not. That's correct, right? Make sense? So we start with like k empty cell, we go to k minus 1 empty cell, k minus 2, k minus 3, eventually we'll hit 1 where everything is filled, or 0, k will be 0 in the end, where everything is filled. The only thing left for us is to check if it's a valid Sudoku or not, right? That would be our base case. Is it clear? Yeah, okay. So this is the pseudo code for this one. Oh, I have two pseudo codes on the slide. I think this one is better, yeah. So the pseudo code, it will go like this. We first choose a random blank cell, and we check if all the cells are filled. Then we simply check if it's a valid thing or not, and we simply return true or false based on that. If it is not completely filled, then we have to check for each and every possible actions at that particular place, right? So we'll iterate from 1 to 9. We'll check if, so we will fill the cell ij with that particular num, and then we will solve the Sudoku for k minus 1 remaining empty cells, okay? If it is returning true, well and good, we solved it. If it is not returning true, that means there is something that where the algorithm made a mistake, right? that particular num is not a suitable num there. So what we'll do is we'll simply mark it unmarked. That means we'll make it blank and we'll go again in this for loop and we will replace it with the next number. Yeah? Does that make sense? So that's how backtracking work. So in backtracking, you start from a position, you go and check for everything. If it doesn't work out, you go to the first decision that you made that was wrong, you make it unmarked, and then you choose the next action that you can take at that place. So that's what basically a backtracking algorithm is. Okay? So if there is a true statement somewhere, it can be written at two places, right? It will be here or it will be here, right? But if you're not able to like get a true thing at either of these positions, you will simply come out of that loop and you will return false, right? Any questions in this one, this algorithm? You can use any heuristic or in a best case scenario, what you can do is like you can maintain an array of size k, and at each time you pick a particular thing and you keep moving it. That is also possible. That you can also do that. But in random, the problem is like what will happen is like it is doing randomly, right? So it might choose a cell which is not empty, right? If you are meant, yeah, that works. That works. Mm-hmm. I don't think it will be faster in that case because we are assuming that choosing is a constant time operation. Choosing an empty cell is a constant time operation. That's what we are assuming. Or what you can do is like you can store this empty cell in an array, and you start with the first empty cell. You fill this, then you move on to the next one. You keep doing this until all the cells are filled. Yeah, exactly. Yeah. Mhm. Oh, so you are trying to eliminate the options. So you are saying like how many possible things can enter that particular place? That's actually an optimization, but in this problem, we are not actually keeping track of like how many possible solutions are there for a given cell. Like nowhere we have stored like how many possible solutions are there. This is a very general algorithm. But if you want to do it that way, like you keep track of like how many possible solutions are there without eliminating the wrong calls, then in that case, I think min heap would help. But then you will have to like change your algorithm a little bit. Yeah. Because right now what we are doing is we are checking for each num from 1 to 9, right? But somehow if we have a mechanism to know like which elements cannot be placed in that cell, then in that case we can use that. Then we can choose the most optimized blank cell, which has like smallest number of possible things that can fill. Yeah. In this case we are doing an exhaustive search. We are checking everything that can be placed in that particular cell. Yeah. Any other question? I hope that explains a little bit. So it's not exactly like we are not actually keeping track of like what are the valid possible solutions, what are not. We are exhaustively trying out everything that can be filled in that particular space. Okay. So how do you prove this? Like how do you prove it is correct? So we start with k, and then we go to k minus 1, right? And we have a base case. Does that sound like induction, something like that? Right? Uh, can you explain that a little bit more? Yeah. That's right. On the empty cells. Yeah. So that's right. We will induct on, like, we will assume like it is giving correct output for k empty cells. We start with k plus 1. We fill that empty cell and we end up with k empty cell sized Sudoku. And by induction it works for that one. And we are checking out all the possible things that the empty blank cell can take place. So that's why one of them have to give us a right solution. Let's see that. So in base case we have 0 empty cells. In that case we simply check if the Sudoku is valid or not, right? And we'll return that, true or false, based on that. And in induction hypothesis, what we are saying is we are assuming that Sudoku with k empty cells is correctly solved by the algorithm. So what we do is we start with k plus 1 empty cells. We pick one cell at random or using some heuristic that you want to use, and then after filling it we end up with k empty cell Sudoku, and by induction that's correct, right? And the ith cell we are checking out each and everything from 1 to 9, so it's an exhaustive search, so that's why the algorithm has to be correct. Does that make sense? Okay. So what's the runtime? Try to create a recursive function in terms of t of k and t of k minus 1. So what happens? So what I want is this thing here. What will it be? So for every k, how many recursive calls are you making? Yeah, that's right. So it will be 9 t of k minus 1, right? And some constant amount of operations, right? Is it clear? So what will it be? So what is t of k? I don't think you can use master theorem here. So if you unravel it, what will it be? I will wait for your response on this one. Yeah? So I didn't get it, sorry. Yeah. There is 9 t k minus 1. If it was 1, then it would have been linear. Yeah. Sorry, what did you say? 9? Yeah, that's about right. Almost, yeah. So it will be something like c times 9 to the k. The c thing will also come there, right? So like every time you unravel k minus 1 will be k minus 2 plus c, and that 9 thing will be added, right? Similarly for k minus 2, one more 9 will be added. This 9 will be added for k number of times, right, in the power. So yeah, so it will be c 9 raised to k and operations. And in our backtrack algorithm, for every cell, for every empty cell, how many cells do we check to check if it is consistent? We check row, column, and the grid. So how many indexes are these? How many cells are these? It will be 24, right? 8 horizontally, 8 vertically, and 8 in that small grid, right? So for every cell, it's 24. That's a constant number of operations to check if it's a valid thing. Make sense? Any questions? I hope everyone is clear about this thing, why it is C9 raised to k. I can explain that if you have any doubts, but I think if you unravel it, you will get the solution for this one. So let's see a general case Sudoku. So now we initially we restricted our Sudoku to 3 cross 3 smaller grid, that is 9 cross 9 bigger grid. So let's say the smaller grids are m cross m. Okay, so we are looking at this Sudoku, m square cross m square. Okay, so in that case, the algorithm would be bounded by O of m raised to 2k, m square raised to k, that is m raised to 2k. Make sense? And the maximum possible value for k is m raised to 4, that where everything is blank, that is m raised to 4 number of total cells. So it is bounded by this thing in worst case scenario. That's not a factorial, it's an exclamatory mark. So, yeah. So one interesting thing which we won't cover in detail today. So Sudoku is generally it is a NP complete problem. Okay. So basically, so there are some classes of problems, and all of the problems like goes through this particular class. Like if you are able to solve this thing, you can solve the rest of the problems. So the Sudoku is generally NP complete problem. Okay. So this is the end for my discussion session. If there are any questions, please let me know.